The Nobel Prize in Physics is typically awarded to scientists who make sense of nature, those whose discoveries render the universe more comprehensible. But the 2022 Nobel has been awarded to 3 physicists who revealed that the universe is even stranger than we thought. This year's Physics Nobel laureates are John Clauser, Alain Aspect, and Anton Zeilinger, who together are responsible for a series of ingenious experiments that proved that the strangest prediction of quantum mechanics is actually true. It's the prediction that Einstein refused to accept. The idea that 2 quantum systems can be entangled, bound to each other, such that they can influence each other instantaneously over any distance. This spooky action at a distance, as Einstein called it, is in seeming violation of his own theory of relativity, which tells us that no causal influence can travel faster than light. Clauser and Aspect achieved the rarest of feats. They proved Einstein wrong, while Zeilinger greatly advanced our understanding and practical application of the phenomenon of quantum entanglement. Of course, we've talked about quantum entanglement once or twice in the past, but today I want to tell you about a series of brilliant experiments celebrated by this year's Nobel. Let's start with a simple thought experiment. You have 2 balls, one black, one white. You close your eyes, shuffle the balls, and place each in an identical box. You put the first box in a rocket and send it to the moon, while you keep the second box with you on Earth. While that box is closed, the ball on the moon has a 50-50 chance of being black or white. You open your box and you instantly learn the colour of the ball on the moon. So, did you cause information to travel faster than light? Of course not. The information about the ball's colours was always there with the balls, you just learned which was which. But now imagine that these are quantum balls with entangled quantum colours. According to quantum mechanics, we not only don't know which is which until the box is open, but the colours of the balls are fundamentally undefined. Each ball is in a superposition state of maybe black, maybe white, until a measurement is made. Opening your box causes the observed ball to have to choose a colour state, which then forces the ball on the moon to choose the opposite. Now you really do seem to have an effect that travels faster than light, with the ball on the moon switching from a superposition state to a defined state as soon as you make your observation. These quantum balls could be any particle from subatomic to molecular scale, and the entangled property could be spin, momentum, or any other quantum property. But why do we have to accept this wacky interpretation? Is there any real difference in the result of the experiment if the colour of the balls is defined at the beginning versus when the box is opened? Why even propose this entanglement and superposition stuff? Well, because quantum mechanics in its standard form says so. Quantum systems are described by a mathematical object called the wave function, which evolves according to the Schrödinger equation. The joint wave function of 2 entangled objects only contains information about the correlation between those objects, not about their specific values. They only gain specific values when observed and the wave function collapses. For our quantum balls to know their own colour the whole time, there would need to be extra information not contained in their wave function. There are a few different interpretations of quantum mechanics that allow this hidden information, and they are collectively known as hidden variable theories. Einstein thought that such hidden information must exist, while others, like Niels Bohr, insisted that the wave function was the complete description of a quantum system. In almost every scientific debate, physicists side with Einstein, but not in this case. Quantum mechanics was just too successful, and Niels Bohr was aggressive in pushing his Copenhagen interpretation. It became dogma, while for a while it was career suicide to question the orthodoxy, for example by researching hidden variable theories. David Bohm got the worst of that with his pilot wave theory, which we talk about in another video. John Stuart Bell was another hidden variable heretic. This Irish physicist didn't necessarily believe in them, but he wasn't content to just accept the Copenhagen interpretation without properly testing it. And he also realized that one could reveal the existence of hidden information without actually measuring that information or even testing a specific hidden variables theory. We've talked about these Bell tests previously if you want to see exactly how this works. In short though, in 1964, Bell came up with his Bell theorem, which shows that there should be a particular statistical correlation between the measured properties of entangled particles if the particles themselves hold the information about their internal states, and a different statistical relationship if those properties really are decided at the moment of measurement. In particular, the so-called Bell inequality would be true if there are hidden variables contained in the particles and violated otherwise. Finally, there was a real test that we could use to check for hidden variables. However, it wasn't until 1969 that the first Bell test was performed, and that was by one of our 2022 Nobel laureates, John Clauser. So why did it take 5 years? Well, Bell tests are really hard to perform. They require the production of entangled states, which have to be manipulated and measured without breaking the exceedingly delicate correlation between the particles. But also, to do a Bell test was to question the status quo, so it was hard to get support for the significant effort required. Clauser talks about the time he proposed his idea for the experiment to Richard Feynman, who promptly kicked him out of his office. Apparently Feynman thought it was pointless because standard quantum mechanics was clearly correct. Clauser and his student Stuart J. Friedman were not to be deterred. They had figured out a brilliant experiment and they were going to try it. It went like this. They blasted a beam of calcium atoms through the intense light of an arc lamp. That light excited electrons in calcium atoms to a higher energy level, and they would then drop down again with the lost energy carried away by photons. One of the possible electron transitions was between two states that had zero quantum spin, and which also resulted in the creation of two photons. Spin is the quantum version of angular momentum. Because the atom's spin hadn't changed in this transition, in order to conserve angular momentum, the pair of photons needed to have a total spin of zero, which translates to them having opposite circular polarizations. Standard quantum mechanics says that those polarizations are undefined until measurement, when they will always turn out to be opposite to each other. Hidden variable theories, on the other hand, allow the polarization to be set at the moment that the photons are created. By measuring those polarizations, by passing both photons through polarizers, Clauser and Friedman could perform a Bell test. Bell inequality was convincingly violated in their experiment, which means quantum mechanics was working exactly as expected, implying no hidden variables, just as Feynman had told them. But the case wasn't quite closed. John Bell himself pointed out that hidden variables could still be a thing, even if the Bell test said otherwise. The result of a quantum measurement depends on how you make the measurement. In the case of this experiment, the orientation of the polarizers determined which polarizations the experiment was sensitive to. Bell's theorem assumed that the choice of measurement is completely free and independent of the particle creation process. But in Clauser's experiment, the polarizers were fixed in position through the whole experiment. Their orientation was already decided when the entangled photons were produced. So what if that orientation had some influence on the polarization direction of the photons at the moment of their creation? Then the photons might carry hidden information about the eventual measurement direction the whole time and sort of conspire to look like standard quantum mechanics, even if they had real hidden variables. To close this loophole, it would be necessary to somehow set the measurement direction after the photons were produced. That sounds incredibly difficult because, in case you didn't know, photons move pretty fast. But when you're a brilliant experimentalist, incredibly difficult is your bread and butter, and so we meet our second laureate, Alain Aspect. Aspect's setup was very similar to Clauser's, with a beam of calcium atoms excited by light, this time a laser rather than an arc lamp. But the main difference was in the polarizers. In order to change the measurement direction of a polarizer, you have to rotate it. But it's kind of hard to do that faster than a photon can travel across your optical bench. Aspect found a way to randomize measurement direction without moving the polarizers at all. The trick was to use a type of transducer, in this case a chunk of quartz, that bends the path of light in different ways depending on whether the quartz is vibrating. And that vibration can be turned on and off with an electrical current. That means our entangled photons could be sent to different polarizers depending on an electrical switch, a switch that could be turned on and off quickly and randomly in the tiny intervals between the creation of the photon and their arrival at the transducer. All of this means that the photons can't know how they're going to be measured at the moment of their creation, which, if you recall, was a potential loophole in the Clauser and Friedman experiment. The Bell inequalities were also violated in Alain Aspect's experiment, dealing another blow to hidden variable theories. So, did Aspect close the final loophole? Not quite. There are two ways that the Bell inequalities could be violated without quantum entanglement being as spooky as Einstein feared. Well, actually, these ways are still spooky, but in different ways. Now, the first loophole I already mentioned, what if the choice of measurement is not independent of the creation of the entangled particles? Aspect's experiment seemed to eliminate that possibility by making that choice after the particles were produced. But what if the random number generator controlling the transducer wasn't really random? After all, signals could have travelled to both the calcium atom and the random number generator from some common influence, causing them to conspire to violate Bell's inequalities. This is the idea called superdeterminism, basically stating that the particles are not only correlated with each other, but also with the random number generator or the physicist choosing the measurement direction. So ultimately, the universe has no choice but to always hide the existence of hidden variables. Now, we've discussed superdeterminism before, so you can decide for yourself whether that's a reasonable idea, but John Bell certainly did not think that it was plausible. But even without superdeterminism, there's another loophole. Bell's theorem can be used to rule out the existence of local hidden variables. It can rule out that the secret information about the entangled particle states lives in the particles themselves. That's what local means here. But there could still be hidden variables that exist in the global wave function of the entangled particles. Clauser and Aspect's experiments ruled out local hidden variables, but that may mean they ruled out locality rather than hidden information. Any violation of locality still means that some sort of influence travels faster than light, the sort of spookiness that Einstein hated. One way or another, our Nobel laureates have revealed a universe stranger than many are comfortable with. Okay, what about our third laureate, Anton Zeilinger? Clauser and Aspect's work was all about testing the fundamentals of quantum mechanics, about getting closer to what its weirdness is really telling us about the world. But their efforts also led to very practical results. They, and others like them, advanced our ability to create and manipulate entangled quantum states. And Zeilinger put these to good use. He may be the most famous for demonstrating quantum teleportation. This is a phenomenon in which a quantum state is transferred between two particles via an intermediate particle that's entangled with them both. We'll save the awesome details for another time. The important thing right now is that quantum teleportation and the corresponding ability to move around quantum information is critical for quantum computers. Zeilinger is responsible for a number of advances in manipulating entanglement and has applied these to quantum cryptography and to the development of quantum computers. This is a rare episode of space-time in which both Einstein and Feynman were wrong. Einstein, because one way or another, the quantum world is indeed quite spooky. And Feynman was right in thinking that Clauser would never disprove standard quantum mechanics, but he was wrong in thinking that Clauser shouldn't try. Because science only moves forward when we try to push its theories to the breaking point. We learn something whether they break or not. And perhaps we find technologies that will be useful in ways that no one could have predicted. In this case, our better understanding of quantum entanglement has brought us very close to the age of quantum computing and quantum cryptography, all because a few scientists were willing to challenge the status quo and seek the hidden secrets of space-time.